Hello everyone, my name is Dhanvantari and in this video I'll be explaining you about data encryption standard, also called as DES, and how to convert DES to 3DES. So the points that are going to be covered in this video are what exactly is DES, what is the working of DES, what is 3DES, and demonstration with an example. So to understand this, we'll be performing a virtual lab experiment. The link for this experiment has been provided in the description of this video. So in this experiment, you are asked to design the triple DES crypto system provided that you are given an implementation of DES. The objective of this system is to understand how to convert a DES implementation to a triple DES implementation. Now let us go to the theory part of this experiment. So what is DES? DES is nothing but a block cipher which encrypts 64-bit of plain text and creates 64-bit of ciphertext, which means that a 64-bit of plain input text is given to this block cipher and it produces a 64-bit ciphertext, which is an encrypted text. So what is the general structure of DES? As we said, that a 64-bit of plain text is given to DES. There is an initial permutation, then there are 16 steps, each step is called as a round, and then there is a final permutation. The final permutation produces a 64-bit of ciphertext. So let us see how the initial and final permutations exactly occur. In the initial permutation, the 50th bit of the input 64-bit plain text becomes the first bit, as you can see in the initial permutation table here. The 50th bit becomes the second bit, and so on. And in the final permutation, the 40th bit becomes the first bit, the 8th bit becomes the second bit, and so on. Now let us understand what exactly happens in each round of DES. So this is the general structure of a round of DES. The 64-bit text which was obtained after the initial permutation is divided into two halves, the left half and the right half of 32 bits each. The right half of 32 bits and a key of 48 bits is given to a function of DES. It produces the output of a 32-bit text, and this output is then XORed with the left half, and then the output is swapped with each other, and this output is provided to the next round. We'll see what happens exactly in this function and from where is this 48-bit key generated. First we'll see from where is this 48-bit key generated. Remember that I told you that DES block cipher uses the 56-bit key. So now this 56-bit key is divided into two halves of 28 bits each. And on each half, circular shifting is performed. The shifting depends on the number of rounds. So suppose if the round number is 1, 2, 9 or 16, 1 bit shifting will be performed. And on all other rounds, 2 bit shifting will be performed. And after this shifting, these bits are given to the compression P box and 48 bits of a key is produced. And this key is now used for round 1, and similarly for every round all these keys are generated and they are used. So we saw how this 48-bit key was generated. Now let us understand what happens exactly in this function. So the broader level steps in this function are the right half, which is of 32 bits, is given to the expansion P box. The expansion P box expands these 32 bits and produces 48 bits. These 48 bits are then XORed with the 48-bit key, which we have seen how it is produced. Then this 48-bit output is given to S box and it produces a 32-bit output. 32 bits are then given to straight permutations to the straight P box, and 32 bits of permuted ciphertext are produced. Now this is the output of this function, the 32 bits which are produced from the straight P box. Now these 32 bits are XORed with the left half and then the outputs are swapped. Now we'll see one by one how the expansion P box process occurs, S box occurs, and the straight P box occurs. What exactly happens in the expansion P box? In the expansion P box, the 32 bits are expanded to 48 bits in the following way. Now the 32-bit input, which was given by the right half, is divided into 8 4-bit blocks. So these are the 8 blocks of 4 bits each. Now each of this 4-bit block is appended with 2 extra bits, so that this 4-bit block, it now becomes a 6-bit block. So from these 8 4-bit blocks, 8 6-bit blocks are produced. So this 32-bit now becomes a 48-bit. The resulting 48-bit output is permuted using the expansion P box. So now here we have obtained the 48 bits from the expansion P box, as we have seen how it is done. Then this 48 bits are XORed with the 48-bit key. This XORed output is now given to the S box. Now we'll see what happens in the S box. S box, which is also known as the substitution box. The 48-bit input is divided into 8 chunks of 6 bits each, and the 8 chunks are given as input to the 8 X boxes. So there are 8 S boxes in the S box substitution. These 8 boxes are given 6 bit of chunks, and from that each X box produces a 4-bit of output. So combined together, a 32-bit output is produced. So how is the exact structure of each S box? So each S box uses a corresponding 4-row by 16-column table. So in this, so the structure of this each X box is going to be, so each S box will have 4 rows and 16 columns. Given a 6-bit input, the first and the 6th bit are used to address one of the rows, and remaining 4 bits are used to address one of the 16 columns, which means that the first and the 6th bit will be used to address the row number, and the remaining 4 bits are used to address the column number. The location of the table as given by the 6-bit input. So whatever will be the location given, whatever are the 4 bits stored here will be the output for each X box. So in this way, the remaining 8 X boxes also work. We'll see this with an example. Consider 6-bit input to the S box 1, which is 100011. The first and the last bit put together, this and this bit, will produce 11, and in decimal it means 3. So we select the 3rd row. So we'll be selecting 3rd row because in decimal 11 means 3. Now the middle bits are 00001, which equals to decimal 1. So we select the first column. As we had said, that the first and the last bit will point to the row number and the middle bits will be pointing to the column number. So the first and the last bit gives 3 and the middle bits give 1. So we will be selecting 3rd row and first column, which gives us the entry of 12. Now 12 in binary is 1100. So this is the 4-bit output from S box 1. Similarly, you can calculate for other outputs. So now the S box will provide you 32-bit output. These 32 bits are permuted amongst each other in straight P box, and the 32-bit output is now passed on to XOR with the 32 bits of the left half, and the output is later swapped with one another. Now these 64 bits are now passed to the round 2. Similarly, in round 2 the same process happens, and this process is repeated for each round. For 16 times this process is repeated, and then the final permutation takes place, and after that we get our 64-bit cipher text. So this was about the theory part of this experiment. Now let us actually perform this experiment. To perform this experiment, the steps are given in the manual. So just copy this link. Okay. Step 1. To generate a plain text M, key A and key B by clicking on respective buttons of part 1 of the simulation page. So this is the plain text message. This is our key A and key B. So we'll have to generate new keys and new message. So just click on change plain text, change key A and change key B. Now step 2 is enter generated plain text M from part 1 to part 2 in your text to be encrypted decrypted block. So copy this plain text and enter it here. Now enter generated key A from part 1 to part 2 in key to be used block and click on DS encrypt button to output ciphertext C1. This is the first encryption. Let us copy key A, paste it here, and we'll click on DS encrypt. So this is our first encryption and we have obtained C1. Now enter generated ciphertext C1 from part 2 output block to part 2 your text to be encrypted decrypted block. So now this output will be given as a message in part 2. Okay. Now enter generated key B from part 1 to part 2 in key to be used block and click on DS decrypt button to output ciphertext C2. This is second encryption. So copy key B and enter it here and click on DS decrypt. So this output is now C2 and we have performed encryption twice. Now for the third part, enter generated ciphertext C2 from part 2 output block to part 2 your text to be encrypted decrypted block. Now the output of the second encryption will copy and we'll paste it here. Enter generated key A from part 1 to part 2 key to be used block and click on DS encrypt button to output ciphertext C3. This is third encryption, and as encryption is done thrice, this scheme is called as triple DS. So just copy part A key and paste it in the key to be used block and click on DS encrypt. So this is our third output, which is C3. Now enter generated ciphertext C3 from part 2 output block to part 3. Enter your answer here block in order to verify your triple DS. So we'll just copy this, we'll paste it in our answer here. Now we'll see if our answer is correct. Yes, our answer is correct, which means that we have performed all these steps correctly. Let us go to the quiz part of this experiment. In DS, the input key length is dash bits and the plain text is dash bits. We know that the input key length is 56 bits and the 64-bit plain text is used. DA stands for Data Encryption Standard and AES stands for Advanced Encryption Standard. DS has initial and final permutation block and 16 rounds. In DS, the length of each round key is 48 bits. With this, we have reached to the end of this experiment. Thank you for your patient listening.